All right, today we're going to be talking about sound wave properties. The beginning here is just going to be a review, things that we've already talked about. So I will go fairly quickly through these first few things because, again, you already know these. For instance, sound is a longitudinal wave. It's caused by a vibrating object. We have played with these pan flutes now, and so we talked yesterday about how the molecules are colliding inside the straw, and that's what allows the sound to be produced. Because those molecules are trapped inside the straw, there are more collisions, and because there are more collisions, the sound is a little bit louder. You can touch your throat, talk to your neighbor. You'll hear those you'll feel those vocal cords vibrating. Plucking a guitar, playing a piano, playing with a tuning fork, anything, clapping your hands, beating the table, tapping the table. All of those things are going to create vibrations, and whenever there's a vibration, then we have sound produced. Remember that a longitudinal wave is also called a pressure wave. It has areas of high pressure and areas of low pressure, and we call those areas of high pressure compressions and those areas of low pressure rarefactions. So this is an image just to remind you of what a compression wave looks like. You've seen this several times now, so this is not new. And this next image here shows you that the tuning fork is moving. We'll be using these tuning forks next week, but when the tuning fork, you can't necessarily hear the frequency of the tuning fork in air, but this is the sound that it's producing. Because the tuning fork is vibrating, it's causing those air molecules to press together and spread out, and press together and spread out. And when that happens, we get those high pressure areas called compressions and low pressure areas called rarefactions. Okay, so again, just a reminder of what a compression wave looks like. Frequency is also not a new word. Now we have related frequency to this new word pitch, which we'll see a definition for in just a minute. But remember that frequency is the number of vibrations per given amount of time. So generally, because the second is the SI unit for time, we're going to refer to that unit of time as seconds. It could be number of waves, number of oscillations, whatever it is that's repeating itself in some given period of time, that is the frequency. And so yesterday when you played with your pan flutes, you recognized that a low tone or a low sound is a low frequency. By using our wave equation and relating the length of the straw to the sound that we were hearing, we were able to identify that frequency and pitch were also related, and in that way they were directly related. So we said that the higher the frequency, the higher the pitch, and the lower the frequency, the lower the pitch. So this means that frequency and pitch are directly related. When we use that word, and to make it a little bit easier to recognize, we can substitute that word pitch in for frequency when we talk about specifically about sound. And then we also looked at wavelength yesterday. So when you take a look at your pan flute, remember that the longer straw had a lower frequency, and the shorter straw had a higher frequency. And so what was happening inside that length of straw is that it was producing a wavelength, or the distance between two areas of high pressure and two areas of low pressure. And we know from our previous unit that wavelength and frequency are inversely related. That's how we came up with that idea yesterday, that pitch and frequency meant the same thing. When one went up, when the wavelength went up, the frequency went down. So when the straw got longer, the tone got lower, and vice versa. So a short wavelength resulted in a high pitch. A long wavelength, a long straw, resulted in a low pitch. Okay, so that is just a kind of a recap of what we looked at yesterday. Now you have some concept questions there. There are 5, so take just a minute and look over those. Answer those with your neighbor. Okay, you should be able to answer these pretty easily. The first one says that sound is a longitudinal wave. Number 2, sound requires a medium, that is, it is a mechanical wave. It has to propagate through some substance. Number 3, sound travels fastest in solids, slowest in gases. Number 4, wavelength and frequency are inversely related. And number 5, as the frequency of a wave increases, the pitch increases. As the frequency of a wave decreases, the pitch decreases. Again, that's that direct relationship, pitch and frequency, the relationship there. All right, so what we're going to look at today, a little bit of new material. We're going to talk about frequency and the human ear. What can you hear? Maybe you've heard of a dog whistle before. What's a dog whistle do? You can blow on that dog whistle and it doesn't affect you. You can't hear it. So that means that a dog can hear differently than we can. And so to identify what that is, our human hearing range is from 20 hertz to 20,000 hertz. And unfortunately, the older we get, that hearing range shrinks a little bit. So we can't, you might have a grandparent or even a great-grandparent who is a little bit hard of hearing. And what's happening is that their hearing range is literally shrinking. They cannot hear as high of frequencies, generally speaking. Two new words that you need to understand. The first one is infrasonic. These are sounds made below 20 hertz. That is below the human hearing range. That's literally what that means. Infrasonic means below human hearing. And then ultrasonic, sound with frequencies above 20,000 hertz, are called ultrasonic. That is above the human hearing range. And there are animals who can hear outside of the human hearing range, and that's how they communicate with one another. So we're going to look at a couple of frequencies now. These are going to warn you that these are high pitches. You're going to it's going to be a noise that perhaps you don't like a whole lot, but we're going to see what your hearing range is. And so we're going to start at 8,000 hertz, that's 8 kilohertz, and we're going to go all the way up to 20,000 hertz or 20 kilohertz and see how many of you can hear all of these frequencies. So here goes the first one. I'll play most of them just one time. So 8,000 hertz. Okay, so rather high pitched, but everybody should have been able to hear that one. The next one we're going to do is 10,000 hertz. Okay, so you should have been able to tell that was quite a bit higher. The next one, 12,000 hertz. Okay, everybody should still be able to hear these. 14,000 hertz. Okay, perhaps might be getting a little uncomfortable for you to hear. Next, we're at 15,000 hertz. Okay, and next, 16,000 hertz. Okay, I'm going to play this one again. Listen carefully. So everybody be quiet. Listen carefully. All right, I cannot hear that one. I'm quite a bit older than you, so it could be, again, that my hearing is diminished. And perhaps some of you can't hear that one. I don't know. We'll go on. We'll keep going, and we'll see if any of you can hear all the way up to 20,000 hertz. Okay, I'll play that one more time. This is, okay, that was 18,000 hertz. One more time. Okay, 19,000 hertz. And finally 20,000 hertz. Okay, I'll play that one more time. And I'd be super surprised if any of you could hear that one. So that gives you this idea of range, that is within the human hearing range is that highest one, 20,000 hertz. But again, the older we get, the less we can hear. What we can hear, though, is amplitude. When you turn up the volume. Now imagine that if I had turned up the volume on that, then it would be a high frequency and a high volume. And we've talked about using our pan flute yesterday, how we could make the sound louder. To make the sound louder, we had to blow harder. If you're blowing harder, then you have supplied more energy to your vibrations. And so amplitude is determined by the amount of energy that's put into the wave. So just like when we talked about amplitude before, the higher the amplitude on our transverse wave meant that there was more energy in that wave. And so the human ear is sensitive to certain pressures, and amplitude can also affect our hearing. If we walk around listening to extremely loud music, or we're in a job position where there's extremely loud construction noise, or perhaps people who work at the airport on the tarmac, they're going to need hearing protection to protect their ears from these loud noises. And so Literally, amplitude is related to the loudness or softness of the sound. The louder the sound, the more amplitude, the more energy. The softer the sound, the less amplitude of the wave, the less energy is being transmitted. And we can measure that loudness of sound by what's called sound intensity, and that is a measurement of how much energy is passing a given point. And so when we look specifically at sound intensity, we're measuring in what's called decibels. So that's a new unit for sound intensity, that is decibels. And decibels, for you to have some idea of the decibel level, in this room right now, if you sit and be as quiet as you can, we're going to be still at about 10 decibels. A whisper is like 5 decibels. So as soon as you start multiple people whispering, then that sound intensity goes up, because again, the combination of those sounds builds the amplitude of the sound waves in the room. But you can see here how it goes up. An automobile, an outboard motor at 50 feet away is pretty far up there. A truck at 90 feet away is pretty far up there. A jet plane taking off 200 feet away, the threshold is just below our threshold of pain. If we add numbers to this, we'll see that the increase, the decibel level increase, is a 10 times mathematical relationship. So every time you go up by 10 decibels, you're increasing the loudness by a factor of 10. So if I increase my decibel level by 10, then I would consider that to be twice as loud as the original sound. So when we look at a chart here, you don't have this one on your paper, but just so you have an idea that normal breathing, again, this one actually, I guess that whisper was from 5 feet earlier, but 10 decibels, 20 decibels if we're whispering, excuse me. A busy street is 70 decibels. Your iPod or whatever you listen to your music on, at maximum level, 100 decibels. So if you look along the right-hand side of this data table, you can see that it's increasing by a factor of 10. For every 10 decibels I go up, I'm increasing by a factor of 10. So if I go up from normal breathing to normal conversation, I've gone up 100 times. So 10 times 10 times 10. That's how much louder it is. Our threshold of pain occurs at 120 decibels, and a jet engine, if we're not far enough away, is at 140 decibels. That would be over our threshold of pain. And perforation of your eardrum, that means a hole is actually forced into your eardrum because of the pressure waves at 160 decibels. Now, there are other reasons that you could have a eardrum perforation, but one of them is the loudness of sound. So you have to be very careful. If you're walking around listening to your music with your headphones in at maximum level day after day after day, then you're probably actually doing damage to your eardrum or to your ear, to your hearing. So keep that in mind. And there are some ways that we can decrease that sound intensity. We can put earplugs in. Some of us, you might use earplugs on a regular basis for particular activities or events. Cotton balls will decrease the sound intensity just a little bit. If I had some, could pass them out. You could do that. Just covering your ears changes the sound level, protects your ears just a little bit. You'll see mothers covering their infants' ears at loud noises just as a protection mode. If you go to a NASCAR race, or if you are, I'm sure when you go to concerts you don't put in earplugs, but perhaps some of the workers who work at concert events would wear some sort of hearing protection because it's something that they are taking part in day after day or week after week, but much more frequently than we do. There are soundproof materials that help weaken the pressure fluctuations. We've talked about soundproofing just a little bit, but when that happens, it means that the extra energy is being absorbed into those materials, and because it's being absorbed, that energy is changing forms, and generally that form of energy is thermal energy. So those materials would be warmer or would warm up. So that gives you some idea then of what sound intensity is. Now, just like with our characteristics, so a sound wave has a high energy area, a low energy area, has a wavelength, has a frequency, just like the basic wave characteristics that we talked about in the last unit. Sound waves also have the same basic wave behaviors. So there were 3 wave behaviors that we talked about. We talked about reflection, refraction, and diffraction. And so we're going to see how those also occur with sound waves. So the first one that we're going to take a look at is reflection. Reflection, we already know, we're associating this word bounce with reflection. When we talk about reflection of a sound wave, it's an echo. And there are echoes going on all the time. Anytime a sound wave bounces off another medium, there's an echo. So even in this room, as you talk, the sound bounces off the wall. However, we don't hear it as an echo because of the distance determinations. And we don't need to hear it as an echo. Animals some animals use echolocation. Bats use echolocation. Whales use echolocation. Dolphins use echolocation to locate prey and to locate each other so that they are able to determine the distance between another animal, the distance between their prey. Echocardiograms are a means of listening to a heart rate. Sonogram is used for soon-to-be mothers so they can hear their baby's heartbeat inside the womb. So that, if you've ever heard a sonogram before, that's the baby's heartbeat. You can literally hear the baby's heart beating inside the woman's womb. But most interesting, we're going to watch this video clip about a young man who is able to echolocate. And he is truly an extraordinary person.
I just recognize.
So this young man, just to give you a little bit of background about him, he was found to have cancer when he was born, when he was a baby. And that cancer was in his eyes. So his mother, at that very young age, had to decide whether or not to fight the cancer by leaving his eyes in or having them removed. And so she chose to have all of the cancerous cell removed. And because of that, the boy now has artificial eyes. And so we're going to watch this clip and find out how he gets around using echolocation.
Is that, he was paying more attention.
Ben's super sense amazed everyone, but this was just the beginning. When he was 7, Ben discovered a new power. He began to click.
For a couple of years, it was just a habit. And then next thing you know, it was making things more distinguished for me. I was able to navigate easier and know what things are.
Ben learned to bounce his clicks off objects around him, giving him an even clearer picture of his surroundings.
When he was very young, I used to always tell him, Ben, make your sound. Even when you're running and playing, don't forget to make your sound. That's his survival technique.
Over the years, Ben has developed his clicking into such a fine art that he can skate freely. He has the confidence and fluidity of movement through space other blind people can only dream of. Ben can see this gap in the parked cars, turn into it, and go through without touching the sides, then smoothly turn again along the pavement. He's entirely self-taught.
Looking at these skills that he's developed with his own mind, I mean, that's got to be really amazing. Somewhere in there, it's a little genius going on.
Ben's super sense has extended his horizons. Clicking has set him free to live life to the full. There's nothing his friends do that Ben won't attempt and conquer.
Oh yeah, that's a shame. Get beat by a blind man in a video game.
Everyone who meets Ben just can't believe their
I'm gonna
eyes.
guess what you had for lunch, okay?
Dr. James Rubin, Ben's eye doctor, has treated many blind children, but Ben was way outside even his experience.
One day I came into the exam room and there was a boy feverishly playing his Game Boy.
He looking at me like tripping out, like, is he really playing this?
I looked at him and I looked at the chart and I said, this can't be the same boy that had lost both his eyes when he was a child. It just can't be possible.
I said, oh, yeah, he's blind. He said, well, how is he playing the video game?
From that point on, I was just flabbergasted.
Dr. Rubin was so astonished, he told the local press. Soon, Ben was swimming with dolphins for a photo feature in People magazine. Then TV news features launched him onto the Oprah Winfrey Show. Like Ben, dolphins echolocate with clicks. They also have highly evolved hearing. The question is, have Ben's ears become super sensitive to compensate for the loss of his eyes?
Pie.
Pie.
He. Smooth.
Smooth.
Book.
Book.
Ben is having a hearing test. Does he have the hearing of a dolphin or bat, picking up frequencies above or below the normal human threshold?
Normal hearing is from 25 decibel and above. And as you can see, Ben has normal hearing in both his right and his left ear.
Ben's ears are not super sensitive, so how does he get so much information from them? Can Ben have trained his brain to translate the sound he hears into visual information? Some of the best listeners in the world are to be found in San Diego in Southern California. At the U.S. Navy submarine base, sonar operators learn their craft.
Now, snapping shrimp sounds like bacon frying in a frying pan. Whales sound like whale sound. And you have boing fish, they sound like boing.
On the surface, a submarine has many ways to see where it is: radio, radar, GPS, and sight. Once submerged, these are all useless. The captain and the crew are blind, but they can still hear. Like Ben, a submarine crew sees with sound using sonar.
Sonar is an acronym that stands for Sound Navigation and Ranging. It's basically the art and the science of using sound to interpret how an object moves and how far the object is away from you.
When an enemy submarine is trying to hide, it goes into stealth mode, silent running. Making no noise, it is invisible to a pursuing sub. To locate it, the hunting crew must throw out a sound and listen for where the echo comes from. Just like Ben when he clicks, they are actively searching out an object with a sound.
When it bounces off a metallic object, it does make a sound like a bell ringing. So you'll hear the ping going out and a ping coming back towards you. And once you hear that sound, you know that there is an object out there that you need to investigate further.
Sonar operators undergo extensive training to interpret the echoes, to discern distance, direction, size, and shape. Remarkably, Ben has trained his brain to do the same, without the help of a submarine's multi-million-dollar technology. In water, even a small noise can be heard for many miles. In air, echoes are much harder to pick up. They're so faint, it's a miracle Ben can echolocate at all. South of Sacramento, between the mountains and the Pacific Ocean, is the University of California, Santa Barbara. Scientists here want to study how Ben sees and navigates with such a faint signal.
Nicholas. This is Ben. Nice to meet you.
Psychologist Dr. Nicholas Giudici has been blind from birth, and geographer Dr. Jim Marston is partially sighted. Professor of Psychology Jack Loomis is the odd man out. He can see. Their research combines psychology and geography to help develop practical mobility aids for the visually impaired. They've invited many blind people to help them over the years, but never anyone who echolocates like Ben.
One that really impressed me was when he walked along that curved path. He wasn't always right in the center, but he did extraordinarily well.
And we didn't even tell him to try to stay in the center. We just told him to walk. We didn't...
You know that it was a curve.
Right.
You did exactly perfectly.
Dr. DeGiucci wants to find out whether he can locate a tree by clicking.
Tell me to find one. Do a click. Is that too high? I'm trying to find another one. Click, right? No.
My clicking is definitely the click of an amateur. I haven't ever done echolocation, so you can hear my clicks and Ben's clicks. They're really quite different. Ben's laughing. Mine are kind of a much less of a full spectrum click.
In the Human Behavior Lab, the tests begin. Exactly how clearly can Ben see with echolocation? First, the team ask him to measure some simple objects.
Can you tell us how big it is without touching it?
About this high.
Next, the researchers investigate whether the faint echoes are enough to build a clear mental picture.
Hit one of the things.
Which two objects are the same? Seeing with light, it's easy, but the tests are proving it's not so straightforward to see with sound.
Oh no, this one.
Yeah?
What's this?
Yeah, that's great.
Good job.
Can Ben go one step further and identify the next thing he finds?
What's that?
You're pointing to it, right?
Yes.
Do you know what it is?
No, I don't know what. No. I know I smell something.
Just like submarine sonar, Ben's clicks can detect an object but not see what it is out of context. The team press on, pushing Ben to the outer limits of his ability. The rod is a very small target to find, and it's also curved. The curved surface of the rod scatters the click. There is hardly any echo returning to Ben's ears. The audio signal is very weak. Can Ben see it at all?
It is little. But just take your best guess as to where you think it is. Just point at it.
Is it right over here somewhere? Touch it. I don't know what you're talking about. That is very, very little.
So we didn't know how big an object you could sense or how small an object.
I sensed
And
it.
this is
I heard it. I
very,
just didn't know what.
but we were, that's the biggest one we were going to try. And then we're going to try some really small ones. And this is pretty much at the limit.
All right, so that's a very interesting video about what can be done. We all evidently have that ability, and this young man was able to see without his eyes, so that's pretty extraordinary. So he was able to identify those echoes in situations in which we, of course, cannot. But as it showed you, he doesn't have any kind of extraordinary hearing. He's learned to use those senses a little differently than we have out of necessity. So reflection, that idea of an echo, a bouncing back of the sound wave. The next type of behavior, just real quickly, is refraction. Again, we have studied this. We know that refraction means the bending, so that's the word you're going to associate with refraction, the bending of a sound wave when it goes from one medium to another. And when that happens, we have noticed, we've talked about already, that the wave speed changes. So remember when we put the straw into the beaker, the straw looked bent, and that was because the wave speed was changing as it entered a new medium. This also happens with sound. Sound changes, the speed of the sound changes and becomes a little bit distorted as the temperature changes. Now, it's typically very unnoticeable for us because the speed doesn't change around us very often. The temperature doesn't change very dramatically. But when sound moves from warmer areas to cooler areas, refraction occurs, that bending occurs. So if you have an idea of what it means to have cool air versus warmer air, particularly here in the South. When it's warm, it's often also humid. And part of then the speeding up of the wave is because it's encountering more water in the air as well. But that's trapping the heat, causing that speed to increase. And then the last sound behavior is diffraction. Diffraction occurs when sound waves pass through a barrier and spreads out. So again, same behavior. Now we're going to look at it specifically for sound. And so diffraction occurs when waves pass through that opening and spread out. Low-pitched sound waves travel farther than high-pitched sound waves, and because of that, animals can use it for communication because those low-pitched waves travel a lot further, particularly animals who travel over long distances can use that diffraction, that bending of that spreading of the wave to identify where other animals are. Elephants tend to use that. They use several different things, and we'll watch that video at a later date. But the last thing we're going to do to wrap up today's notes is talk about velocity. These things are already on your notes. No need to fill anything in. We know these things. We've talked about them previously, but just as a reminder, sound, velocity of any wave, but sound travels faster in liquids than in air. Sound travels faster in solids than it does in liquids. And why is this? Again, because sound occurs because the molecules are colliding. When molecules are in a gas, those molecules are farther apart. When they're in a liquid, they get closer together, and in a solid, they're very close together. And so more collisions can take place. Sound does not travel through a vacuum. Why not? Because there are no particles to propagate that energy. There are no collisions taking place. So sound cannot be propagated. And the last thing we're going to look at here is this equation. This is going to be a new equation for us. And it has to do with that change in temperature, that warmer area we just talked about, causing an increase in velocity or an increase in speed. And so as temperature increases, the velocity also increases. We're going to use this equation. Again, V is still the velocity of sound in air measured in meters per second, and the T represents the temperature of air in degrees Celsius. So V is equal to 331 plus 0.6 times the temperature. What that means is that at air temperature, 20 degrees Celsius, sound travels at 343 meters per second. That is an accepted value for the speed of sound, 343 meters per second. And we're still also going to be able to use our basic wave equation, the one we've already studied, where the velocity is equal to wavelength times frequency. The velocity is measured in meters per second. Wavelength is measured in meters, and frequency is measured in hertz. So this is not a new equation, very familiar. You can use either of these equations based on what the problems are asking you to find. So you have 3 example problems down there at the bottom of your sheet. I would like you to try those. You should have a calculator with you today. So if not, we'll get a few out here. But sound travels approximately 340 meters per second. What is the wavelength of a sound wave with a frequency of 20 hertz? Number 2, what is the speed of sound traveling in air at 20 degrees Celsius? And number 3, if the above sound wave has a frequency of 261.6 hertz, what is the wavelength of the wave? When you have those answered, the teacher will come around and check your answers, and you have some practice problems to be working on for the remainder of the period today.